Swayam Prabha. Digital India. Educated India.
Well, if you have not seen this stuff, there's a lot of fascinating patterns here, and you should do it. You should read about groups. But for this lecture, we don't really need a lot. I'll give you one more example, though, and that is the Zn star, the group Zn star. Here, we are working modulo n, but that star indicates that we are going to use multiplication as the group operation. Now, that's not so straightforward because if you're using multiplication, the identity element is 1. That's fine, but not every element is going to have an inverse. In particular, 0 times anything is 0, so you cannot make it 0. 0 cannot have a multiplicative inverse. So the only elements that are allowed here are elements which have multiplicative inverse modulo n. And another characterization of those numbers are the elements which are co-prime with n. Okay? Again, if you have not seen this before, you should, when you get a chance, look it up. But for now, you just can take it for granted that in Zn star, the elements are all the elements that are co-prime with n. Okay? And they have multiplicative inverses. So I think I might have an example here. Actually, I'm going to have an example, but it's for a special case where n is prime. Okay, when n is prime, every element is co-prime with n, every element smaller than n, right? Apart from 0, right? So all elements 1, 2, 3 up to n minus 1, they're all co-prime with n. And so here is an example, Z phi star. So all of those elements, 1, 2, 3, 4, are co-prime with 5 because 5 is prime. And I'm claiming that it is a cyclic group. Okay, so in this case, the cyclic group, the multiplication is the operation. So I have one generator here, 2. So what is 2 to the power 0? It's 1. 2 to the power 1 is 2. 2 to the power 2 is 4. And 2 to the power 3 is 8. But modulo 5, that is 3. And that gives you all of this 1, 2, 3, 4. Right? So 2 is a generator, as is 3, and you can verify. 1 and 4, 1 cannot be a generator, right? It's identity. You raise it any number of times, you stay there. 4 is not a generator, it is actually minus 1. So it just switches between 1 and minus 1 as you go through its powers. So they are not generators. So this is a very useful example if you want to have a prototype for well, not prototype, but if you want to think of a cyclic group, Zn star is a good example. There are other cyclic groups also, or rather, let me say, Zn star is cyclic for other n's also, but prime is probably the most useful thing for our purposes, prime n. Okay, so those are just examples. We are not going to use them right away. What we need from a group is that this group operation should be something efficient. If it was some multiplication modulo some number or addition modulo some number, clearly it's efficient. But there will be other groups that we would mention, and they're it's not as immediate that the operation is efficient. So we do want that. Okay. Also, we want it to be efficient even though the group itself will be really big. So think of each group element as being represented by roughly k bits, 128 bits or so, let's say. And so there are 2 to the 128 such elements in this group. So it's a really huge group. You cannot have a table for the multiplication for lookup, but there should be some efficient algorithm to do it. Okay. Okay, I've not talked about this aspect of things, so I'll skip it. We are always talking about a security parameter and asymptotic security. As you increase the security parameter, how good how hard problems get for the adversary and so forth. So you can ignore this thing because I have not tried to avoid this so far. So I'll just pick a group, but of course it's coming from some family of groups. And so it's a family of groups. There will be many groups. Even for the same size, there are many groups. So you need to pick one group out of it often. Okay, so you would have some notion of generate a group, pick a group from this family. And or pick a generator for this group. That's another thing you might want to do efficiently. I already mentioned this. The size of the group will be exponential in the representation of each group element. We want that representation to be big enough. 128 bits or so, security parameter. 128, 256, 512. There are all sorts of numbers that will be needed for specific when you're working with specific groups. Okay, so we need I already mentioned, we need efficient algorithms for generating the group itself. Also, we need efficient algorithms for adding, inverting, and also randomly sampling a group element. Okay, so these are all things we'll need from a group. Now, so once you have a group that you can efficiently work with, we also want some things which are hard in that group. Okay? So we won't usually be talking about addition modulo n as our group operation because there is pretty much nothing that's hard there. But we'll be interested in groups where some problem is hard, and in particular, this problem called the discrete log problem. Okay, so what is the discrete log problem? So it's like logarithm with respect to some base, but the exponentiation here refers to what's happening in the group. Right? This g to the power x would mean x is an integer here, and g is a group element. So g to the power x would be g times g, x times, right? So the discrete log problem is that I will give you a generator of the group. So g, so it's a cyclic group. It has a generator. I'll give you that, and I'll give you a number x, not a number, a group element x, capital X, and you have to return me a number, little x, such that this capital X is g to the power little x. Okay, so if we just ask for this, right, given x equal to g to the power x, find me a little x which is, find me little x. That is the logarithm of capital X to the base g. Right, that's what we do in real numbers. So we just use the same terminology here. But now it's a discrete world. It's a finite set of numbers here. So we ask for the discrete logarithm of capital X, and that's supposed to be little x. Okay. Now this problem of this actually what we are interested in is making this a one-way function. So it should be easy to compute the exponentiation, and it should be hard to invert. That's what we are going for. So first thing is let's just make sure it's easy to compute in the forward direction. It meaning the exponentiation is easy to compute. So how do you do exponentiation in a group like this? So what I told you is I know how to do multiplication, right? So I'm using the multiplicative terminology. So I know how to do multiplication efficiently. So I give you a group element g, and I'll give you some number x. X is some number in this range. And you have to give me g to the power x. How do you do it? So why not just take g, multiply with g, you'll get g squared, multiply with g again, you get g cubed, and so forth. What's that again? I could do multiplication n times, right? Well, just think how big this n could be, or how big this x could be. I told you that the size of the group is exponential in our security parameter. So it could be 2 to the 128. So I ask you for g to the power, 2 to the 100. You'll have to multiply 2 to the 100 times. And that's beyond your ability, right? So that's not what you want to do. But what you can do is repeated squaring. You do g square, g to the power 4, g to the power 8, g to the power 16, and so forth. You can get to g to the power 2 to the 100 in 100 steps, right? Of course, I might ask you for another number, but you would want to think about how to do it. I can, still in logarithmic number of steps, log n number of steps, I can compute g to the power n, okay? Order log n steps. So that's it's a simple thing, but yeah, it's important to use repeated squaring and then putting things together rather than trying to do sequential multiplication. Okay, so that's the easy part. What we hope will be hard is the backwards, namely the discrete log computation, right? So given capital X and G, find little x. And that depends on the group. There are, of course, groups where it's easy, like the additive group modulo n. But hopefully there are other groups where it's hard. Okay? So the assumption, it's an assumption we are going to make about the group. So the assumption states that if I did this experiment, I generated the group. So it's an assumption about a group family, to be precise. I generated the group and the generator. And I picked a random element from the group. Okay, so this is a cyclic group. And the adversary is supposed to find me a z such that g to the power z is x. So that's the discrete log, right? And the assumption is that the adversary will have negligible success probability in this experiment. Okay. May or may not be true for a particular group. Now, if that assumption is not true for a particular group, namely you have a reasonable probability of finding the discrete log, then this Diffie-Hellman key exchange we are talking about is not going to be secure, because I give you the adversary says g to the power x, and there's a reasonable probability that it can find x, or maybe a not so tiny probability that it can find x or y. And once it knows x or y, it can compute g to the power x, right? So if the adversary, the eavesdropper, gets little x or little y from g to the x or g to the y, then she can compute g to the x. Okay. So discrete log assumption is a must, or it must hold if that little protocol we saw has any hope of being useful as a key exchange.
Sir, while computing g to the power x, so the x is coming from the group?
No, x is an integer, g is in the group, g is the generator of the group, x is just a number saying how many times you are supposed to multiply g with itself. Okay. But yeah, what I was saying is that you don't compute it by multiplying with itself so many times. Any other questions? If the discrete log assumption is broken, then it's a key recovery attack in the sense that the adversary can find the key based on the transcript there. But that's not good enough. That's a necessary assumption, but not sufficient for the protocol to be secure. And what's sufficient and necessary is this assumption, the decisional Diffie-Hellman assumption. So I already mentioned it, right? G to the power x, g to the power y, g to the power xy is indistinguishable from g to the power x, g to the power y. And the random element can be written as g to the power r. Okay, for a random r. So here x, y, r are all integers in the range 0 to g minus 1. And the little g is an element, a generator for the group. Okay? So that's the assumption we want. And it's at least as strong as the discrete log assumption. It's a strong assumption in the sense that it's possible that it's at least as strong as the discrete log assumption means that if the DDH assumption holds, then it also implies that the discrete log assumption holds. Why is that? You should think of the contrapositive. If the discrete log assumption doesn't hold, then the DDH assumption cannot hold. Because if the discrete log assumption doesn't hold, an adversary can check. It can compute this g to the xy, the third element, right? From g to the x and g to the y, it can try to compute g to the xy. If the discrete log assumption doesn't hold, it has a good chance of being able to do that. And then it can tell whether the third element is g to the xy or not. Okay. So it's at least as strong, and in fact it's possible, or there are groups where we think the discrete log assumption holds, but we clearly know the DDH assumption doesn't hold. An example of such a group is the Z star, where P is a prime number, And there the discrete log assumption is believed to hold, but the DDH assumption doesn't hold. It's not obvious why it doesn't hold, but there's a little thing you can check efficiently. I'm not going to go into that. You can check, check if it's if things are perfect squares or not, and you can use that to distinguish between g to the r and something of the form g to the xy. Okay. So yeah, so it's a stronger assumption, DDH. Nevertheless, there are many groups where the DDH assumption is believed to hold, and these include certain number theoretic groups. So it's working modulo n, but certain kind of n, and not all integers modulo n, only perfect squares modulo n, and so forth. There are also these so-called elliptic curve groups, and that's by far the standard groups currently used for all problems that are using Diffie-Hellman key exchange related things. Or discrete log assumption also, you would find that the elliptic curve groups are the ones that are used, because the discrete log problem is harder in these elliptic curve groups in some sense than in these number theoretic groups. So you can get away with a smaller number of bits, a smaller group size. So now let me actually give you an encryption scheme based on this key exchange we saw. The key exchange didn't have the syntax of an encryption scheme, right? So this encryption scheme is called El-Gamal encryption, but it's basically just Diffie-Hellman key exchange packaged as an encryption scheme. So let's first, think of how the Diffie-Hellman key exchange looks, right? So this is what they do. So to remind you, I just wrote it in slightly different order here. Bob picks random y, sends capital Y. Alice picks little x, sends capital X, and then they derive the key, as y to the power x or x to the power y. Right? Now, to package this as an encryption scheme, the idea is that somehow we will do this and use this key as a one-time pad. Okay? So we have to do this within the syntax of an encryption scheme. The encryption scheme allows a public key, a ciphertext. So it doesn't have everything in this protocol, but the plan is to kind of think of using this key that's there from the protocol. So for now, just imagine there is a protocol. We'll see how the protocol goes away and we get an encryption scheme. But so there is a key that came out of the protocol. You want to use it as a one-time pad. And I've written this kind of curious notation here, m times k. The idea is that m here, the message, is a group element. Okay, or the message should be encoded as a group element using some arbitrary encoding that you can efficiently decode. And then the one-time pad is actually doing the group operation. So earlier it was the bitwise XOR. Well, that is because we were working implicitly with the group of bit vectors. But one-time pad works for any finite group. So you need a random group element as a key or the pad, and you just need to apply the group operation with the message, and you get the ciphertext. So that's something you should convince yourself of, that it makes sense. If you were, say, modulo n or something, you can think it through. But so this what it looks like, the encryption. Okay, so Bob is he can also compute this same key k, and he can so there's a group operation, right? K inverse, so you can efficiently do that and then unmask. So this is something they could do for communication. It doesn't look like a public key encryption scheme. There is no key generation. There is no, there's no encryption that uses that key. So here is how we'll repackage it. Think of this first message here as Bob's public key. So Bob is the one who is the receiver. His secret key is going to be the little y, and his public key is the capital Y. Okay? And whatever Alice is doing here, well, she was sending a capital X followed by a C. All of that together is her ciphertext. So as part of encryption, she will pick a little x randomly and compute this capital X and capital C. Okay, that's all part of the ciphertext. And yeah, so just to write it out, the key generation was, there is also all these group parameters being generated, capital G and little g. That's also part of the public key. To encrypt, you pick a little x and you compute the capital X, and also you compute this m times y to the power x. Right? And to decrypt, again, first you have to compute this capital K, which is x to the power little y. So this notation, I mean, the font may not be very clear. This is supposed to be x to the power minus y. So C times x to the power minus y. Okay. And yeah, so the key generation algorithm is using the group generation algorithm to get the group and the generator, and also picking a little y. Yeah, and similarly during encryption, a little x is picked. They're all uniform from the order of the numbers 1 to order of the group minus 1, 1 to order of the group rather. Yeah, this is what I mentioned earlier. The message is encoded as a group element. Okay, yeah, go ahead.
How is the message encoded as a group element?
Okay, how is the message encoded as a group element? Any way you want. Think of the group. So there is some bit representation of group elements. You could say my message, I'm going to make it exactly that thing, but maybe my message doesn't look like a valid group element. Do whatever is needed to get to the next group element, or so it's arbitrary. In specific groups, you can figure out what's the right way to do it. Okay, but it is it is an annoyance, right? You have to encode your message, a block of your message, as a group element. It's a little bit of a group-specific operation you need to do. So there's another thing that is possible, which is keep your message as a bit string, take this key and convert that into a bit string. Okay. Now you don't want you don't want to take the group elements have some arbitrary representation. A random group element may not give you a random bit string. Maybe always the first bit is 0, or most of the time the first bit is 0 or something in the group representation. So you don't want to just take the group element and use it as it is because of quirks of the group, how the group is represented. So instead you pass it through some key derivation function. And the purpose of the key derivation function, again, we won't go into it in detail, but it's to take something which has high entropy and make it look like something that's uniform. Okay, and usually you would just use a hash function, which is something we'll talk about in the next lecture. Okay, so actually I should pause there for a second in case you have any questions on Elgamal. So Elgamal is our so far our best example for public key encryption, and the DDH is a pretty reasonable assumption. We work with elliptical groups; they're pretty efficient. So we're kind of done with public key encryption to some extent, right? So any questions at this point? Yeah.
When we are encoding the message as a group element, so we are choosing the generator in such a way that generator is to some number. Is the message not representing the message by using the base as the generator?
No. So for the discrete log problem to be hard, you don't want a representation of group elements as this exponent, right? So or exponent for, in some sense it's okay, it will be exponent for some particular generator. And if I pick another generator, the discrete log still would become hard. But yeah, so the representation I'm not making any assumptions about, as long as the DDH assumption holds with your group representation. So DDH assumption is not just about the group, it's about the group's representation also. So yeah, we are not going into any specific groups. So we're not talking about under what representations this assumption can hold. But typically, it's the most natural representation. So if it's integers modulo n, some subset of integers, they'll be just represented as an integer. Does that make sense? Any other questions? Yeah.
Can you repeat the DDH?
The DDH assumption. The DDH assumption was exactly what is needed for this Elgamal encryption to be secure. It says, this thing here, the top line here. That's one line description of the DDH assumption. If you have picked this triple g to the x, g to the y, and g to the z, where z is either xy or uniformly random, you cannot tell the difference which one I did. Okay. Any other questions? Okay. So so this is all good. Elgamal is a very useful and important encryption scheme, but it leaves some room for improvement, and that comes from this notion of a chosen ciphertext attack. Okay, so I have a little story that I will tell you, to motivate this chosen ciphertext attack. Oh, by the way, some of my notation here is not consistent with what I've been telling. So forget that SIM thing. When I say, suppose encryption ENC is a CPA secure encryption scheme. Okay, forget SIM. And so somebody is going to use this encryption algorithm to encrypt their messages, hoping that there will be confidentiality. There is no concern of integrity here in the sense that all the channels are authenticated. So when I get a message from Alice, I know it's Alice who talked to me, right? So that's not the problem I'm going to talk about. But still, there is some attack you can do which affects confidentiality, which completely derails confidentiality. Okay, so I have a couple of characters here, my Alice and Bob. And Alice has written some poem for Bob, right? This message. She wants to send this message. So I have pictures instead of notation. I also have notation on the other side. So this is the thing that Alice sent to Bob. It's an encryption of M. She has a key. She has a public key of Bob. So she used the public key of Bob to do this encryption, right? I represented it as sitting inside an envelope, which only Bob can open. The dotted thing inside is a little letter she wrote. We know it's inside there, but we cannot read it. It's inside the envelope. Now, some eavesdropper, happens to be a hacker, and she takes this message and applies some hack to it. So she hacks away at this function, and somehow she manages to get an encryption of some message M star, again under Bob's public key. So she cannot read what this M star is, right? But this M star is related to this M. Say M star is a reverse of M. Is that something she could do? Well, sure. Suppose this Elgamal encryption was this encryption that I have is Elgamal encryption. Let's say whichever one you want, but applied character by character. That does not affect the CPA security. It will still be a CPA secure encryption scheme. If when I want to send a long string, I encrypt it independently, character by character. With it's a randomized encryption scheme. I can use it any number of times. So that's okay. So that's, let's say, what Alice was using. Alice and Bob are using. Okay. And now all that Eve is doing is just rearranging these encrypted characters, okay, in the reverse order. Okay, so it becomes an encryption of M star, which is where M star is the reverse of M. So far so good. Okay, but this is not a problem, right? She can do it. Who cares? She cannot read it. So all good. Now, suppose, So now suppose she sends this encryption to Bob. Bob knows it's coming from Eve. So Bob receives this little message encrypted message from Eve. intended for him. It's encrypted under his public key. He decrypts it, and he sees this garbage. Okay. So what? Well, now suppose he writes back to Eve, saying, "Hey Eve, you sent me this little thing. Makes no sense to me. What is it?" Right? He just quotes her thing, and sure enough, Eve recovers his message. So it's not. You might say it's not a problem per se of this encryption scheme. The encryption scheme was never broken. You kind of tricked Bob into decrypting it for you. Okay. But what he decrypted was actually not the original ciphertext that Alice sent. It was a different ciphertext, and even the message is different inside it. But by making him or tricking Bob into decrypting messages which are related to M, so from Bob's point of view, he got the ciphertext from Eve. Eve should know what is inside it, right? Or you may know what is inside it. So he might think that it's fine to reply to Eve. But the point is, Eve created this ciphertext without knowing what's inside it, in a way that that message is actually related to something she's interested in learning. Okay, so this is a chosen ciphertext attack where Eve somehow tricked Bob into decrypting a ciphertext that she chose. She chose not just by honestly encrypting, but she created that ciphertext by picking some other ciphertext and manipulating it. Okay, so this is a concern of chosen ciphertext attack, that if the encryption scheme lets Eve do this, create a ciphertext whose message is something, has some information about the message here, then she, even though she cannot decrypt it herself, she might be able to, in the bigger system, get it decrypted by the legitimate receiver. And then that kind of leaks into the system somehow, and she will learn the original message. Okay? So that's a concern of chosen ciphertext attacks. So the specific problem with the encryption algorithm was that it was malleable. The encryption scheme is malleable. What does malleable mean? So malleability is like, you can take a sheet of metal and beat it into whatever shape you want. So similarly here, Eve can take this ciphertext and beat it into a different ciphertext, right? So without being able to decrypt it herself, but she can still manipulate a ciphertext and get another ciphertext. Well, that by itself is okay, right? She has a public key. She could have created any number of ciphertexts which she wanted. But if she is creating a ciphertext using the public key for a message she knows, no big deal, if Bob decrypts it for her. The point is, she might actually take a ciphertext whose message she doesn't know. And so not by honestly creating ciphertext, she might maliciously create a ciphertext from some other ciphertext. And then, the message inside that ciphertext will be related to the original message. That's a concern. Okay, that's called malleability. And El-Gamal is malleable. So remember, this was El-Gamal encryption. You have, so this is what Alice picked, the little x, right? So you have G to the x, and then the key was this capital Y to the x that is used as a one-time pad on this group element M. So this is what the ciphertext looked like. And what Eve can do, so Eve sees this two elements, so two group elements. The first one is G to the x, I'm calling it capital X, and the second one I'm calling C. And she can take those two group elements and create another ciphertext X and let's say T times C, where T is another group element. So what she has done is T times M times Y to the X, right? That's the new element here in her ciphertext. The first one is still G to the power X. If Bob decrypts it, he will get T times M. Okay, so even though Eve doesn't know what the original message is, she can create a ciphertext of T times the original message for any t of her choice. Okay, so that's one kind of malleability in algorithm. There is another kind of malleability. She can raise both of these to some power a, and that'll give you a ciphertext for the message m to the power a for any a of your choice. Okay, so these are all malleabilities present in algorithm. And if chosen ciphertext attack is possible in the system, then Eve can exploit this kind of malleability and recover the message, right? So yeah, so this is something to fix. So we need encryption schemes which will have to be secure even when there is a chosen ciphertext attack. Yeah, go ahead.
So if it is changed to X bar A and C bar A, then how will Bob decrypt because of these?
So okay, I didn't go over it, but what is x power a? It is g to the power little ax. So think of little ax as another x prime. So it's g to the power little x prime. And what is c to the power a? Well, c was this, c to the power a will be m to the power a times y to the power ax, which is y to the power x prime.
So sir, Bob will not know that X prime is now A times X prime.
No, so first element has become g to the power x prime. So I'm sending you, what Eve has constructed is g to the power ax, right? G to the power x prime. Ax I'm calling x prime, right? So now the new ciphertext looks like g to the power x prime and m to the power a times y to the power x prime. So it's a valid ciphertext, just that, instead of x, now it's x prime. Okay. Any other questions? Yeah.
What are the chances that the Eve will successfully crack the message in a finite computation?
Well, she will completely get, if the chosen ciphertext attack is there in the system, in the sense that she can just ask Bob to decrypt whichever ciphertext she wants, and she will ask Bob to decrypt this ciphertext, say x times tc. Once she gets, and she'll get tm. Once she gets tm, she can just divide by t, apply t inverse, multiply by t inverse. And that's efficient.
And what if the m star, that message that the Eve has generated, is completely unrelated to them?
Well, if it's completely unrelated, that's something, that has no information about m, then there's no problem. That's something she could have done herself anyway, right? She could have created, without, even without looking at the original ciphertext, she could have created this other ciphertext of some m prime. Getting that decrypted wouldn't help her. So to exploit malleability, you want to actually, or to exploit chosen ciphertext attack, the ability to launch chosen ciphertext attack, you want to use some malleability. You want to take a ciphertext and beat it into another ciphertext. Okay? If you just create your own ciphertext and get them decrypted, there's nothing you're learning beyond what you already knew. Okay?
Also, sir, decrypting the whole correct message will require multiple tries.
Not in this case. So the question is, from this, will Alice be able to, or Eve be able to get the message fully? In one shot, she will be able to get it, right? She got Bob to decrypt this x comma tc for her, which means she gets tm, and she can divide by t and get m. There's no multiple tries needed. Okay? So if chosen ciphertext attack is a possibility in your system, sometimes it's not, because your Bob will say, I'll only accept one ciphertext using each key. For whatever reason, I throw away my public keys and keep refreshing them. Not a very efficient way of doing things if you are, say, using it as your address, right? For your email ID, somebody has to decrypt it. You cannot keep changing your public key all the time. So there are situations where it's not a concern. For instance, when we'll see later. But there are also situations where it is a concern. Chosen ciphertext attack is a possibility in the system. And in those cases, you don't want malleability in your encryption scheme. So how do you handle, I'll just move on. Okay, so how do you handle this? Well, you upgrade your security definition. So from int CCA, I'm going to upgrade it to from int CPA, I'm upgrading it to int CCA. And it's almost the same thing as before, except now I have added these things. So the adversary gets access to the decryption oracle. Okay, so he can now, so now there is the decryption oracle also sitting here, decryption algorithm also sitting here with the key, with the secret key, and the adversary can query it. Of course, that sounds like a little too drastic, because if he can query it, he could have queried it with this ciphertext he got and figured out what B is. So we will guard this access. We will say, okay, that's the only thing you cannot do. You cannot query this, this particular ciphertext to the decryption oracle. You can query anything else you create, and so in particular, you can take this ciphertext, malleate it, create another ciphertext, and you can query it. But you cannot query just this one to the decryption oracle. And that's just, that, rest of the experiment is the same. This definition, CCA security, may look a little technical, right, ad hoc, but there are alternate ways of looking at this definition, which I won't be going through today, which kind of convinces you that, okay, this captures all concerns when Eve is also sending messages to Bob and getting them decrypted. Okay. It's not so much a concern in symmetric key encryption, or rather, in symmetric key encryption, this concern is completely taken care of once you have authenticated channels, because the secret key that's used between Alice and Bob is not what's going to be used between Eve and Bob. So Eve is not going to use the Bob is not going to use the Alice-Bob secret key to decrypt messages coming from Eve. Right? So as long as you authenticate things, CCA security is taken care of there. Here, that's not the case in public key encryption, because Bob is waiting there with his secret key to decrypt messages coming from everyone. And that's the danger. So do we have CCA secure encryption schemes? Sure we do. Okay, I'm way behind in terms of time. So let me just say there are, under DDH assumption, there is something called Kramer-Shoup. There are many others which are a little more efficient, in particular something called RSA OAEP. And these are secure in a heuristic model called the random oracle model. So let me quickly tell you what the random oracle model is. So it's a heuristic model. So you imagine that there is some oracle in the sky which is a random function. So it almost sounds like a pseudo-random function, right? A random function will show up. It's not, clearly a random function is too big a thing. And it won't show up anywhere. We want it to be a function that everybody can evaluate. It's like a little function call you make to this random oracle. And it's the same function that we are all using, right? And yeah, so you can query it with an input x and it'll return some random value. But of course, if you query it with the same thing, or if two people query this random oracle with the same input, they'll get back the same thing. Okay. Yeah, all parties have access to this. So what is this, modeling? It's trying to model a hash function which has some unspecified properties. We'll talk about hash functions in the next lecture a little more in detail. But here, a hash function is just some algorithm which takes the input and in some unspecified way completely mangles it and produces some output, right? And that's what this random oracle is supposed to model. You give it different inputs, the outputs are somehow completely unrelated, independent of each other. And on the other hand, everybody can efficiently evaluate it. That's what this hash function is. There's a heuristic model, in the sense that, okay, so it's a heuristic model because the hash function is a particular function. It's not some random function that is sitting in the sky. But the hope is that this particular function has no structure in it, that the only useful thing you can get out of this function is evaluate it, like feed inputs, get outputs. Okay, that's kind of the intuitive justification. So if that's all you're going to do, then you might as well imagine that this function is sitting inside a black box, it's sitting in the sky. You're not really looking at the structure of this function. So now imagining that there is instead of hash function, it is a thing sitting in the sky, means your security definitions will slightly change to say that that function is actually picked at the beginning at random. Even though the model is a heuristic model, there is no real justification for it, and there are reasons why it is not good also. It's still a good practice to use this model rather than just saying, oh, here's my construction, I hope it is secure. Instead, now you're saying, here is my construction, it's secure in the random oracle model if you model this hash function as a random oracle. So you're putting all your bets on the hash function having no simple structure. That an adversary doesn't know how to exploit the structure in the hash function, they're only going to use it as a black box. So this gives you security guarantee against those kind of adversaries. Right? It's a widely used tool, so it's good to know about it. But unfortunately, we also, from a theoretical point of view, it's a thing that doesn't exist, in the sense that you cannot make a pseudo-random oracle. Might look a lot like a pseudo-random function. The main difference is that in a pseudo-random function, to evaluate it, you need the key. So there's one person who has a key who can evaluate it, everybody else, it looks random to everybody else. Here, that part is missing. Everybody should be able to evaluate it, and it should look random to them, right? And there are impossibility results, meaning there are schemes or even primitives that have secure constructions in the random oracle model, or that are secure in the random oracle model, which simply do not, you can prove that there is no such secure scheme in reality. Okay, so you can do impossible things in the random oracle model, which is a red flag. So you don't want to trust something you proved secure in the random oracle model because your thing may not be really secure. Nevertheless, as I was saying, it does tell you something, right? The only way to attack this scheme, if it is secure in the random oracle model, is to do some interesting thing with the hash function which nobody has managed to do. Okay, that was a brief detour as to what random oracle is, and there are all these constructions for CCA secure encryption schemes in the random oracle model. There are also ones that are secure in the standard model, just that the things secure in the random oracle model tend to be more efficient. Even though they are more efficient, they're still much less efficient than symmetric key encryption. All of PKE, even the CPA secure ones we talked about, they're much less efficient compared to running a block cipher. Okay, so RSA OAP or Kramer-Shoup or even El-Gamal, they all use group operations, exponentiations in the group, and they are slow. So what people are doing in practice is not to use public key encryption on your actual data. Use public key encryption to transfer a short key, which will then be used for symmetric key encryption. Okay, so now even though public key encryption is slow, you are only using it on a small amount of data, and the actual bulk of the data is encrypted using symmetric key encryption. Okay, and that is that's fast. I'll skip this, I guess. There is a terminology for this kind of use, or public key encryption schemes built with this philosophy. That's a chem-dem paradigm. Chem for key encapsulation method, dem for data encapsulation method. And the chem is basically the public key part, dem is a symmetric key part. But you don't need chem to be a full-fledged encryption, chem or dem to be a full-fledged encryption scheme. So there's some efficiency to be gained. Skip that. Oh, that was the last slide I had, right on time. Okay, so I can take a couple of questions and then we will continue in 15 minutes. All right, otherwise we'll break now and we'll continue in 15 minutes.